Okay, so as I said, guys, I want you to see what we can remember from last week. I would like you to try. Okay, question number 3 there on the board. That is it says distance, but it's actually position versus time. Okay, so it is a position versus time graph. Okay, so I would like you to calculate the displacement from 0 to 4 seconds, the total distance traveled, average speed, and average velocity over the whole trip. Answers are in bold. Okay, you can check if you did it right, and then we'll go through the whole thing here in a minute. But we just want to review position versus time graphs from last week before we move on to velocity versus time graphs. Okay. Okay, so if we want to find the displacement from 0 to 4 seconds, we're simply going to go final position minus initial position. All right, our final position was -4. Our initial position was, what's our displacement? -4 meters. Okay, and then the total distance traveled. That we have to do section by section because we have to add them together. Okay, so we've got in this section here, we go from 0 to -4, so that's how far? 4. Okay, and then we go from -4 to 6. That's how far? Okay, so how far do we go in total? 14 meters. Okay, pretty simple. All right, then average speed and average velocity. So average speed over the whole trip is total distance, 14 meters. We just calculated that. Okay, divided by 6 seconds. Right, so that should give us 2.3 meters per second. And then obviously for displacement, okay, the average velocity over the whole trip, our total displacement is 6 minus 0 over 6 seconds. So our velocity is +1. Positive. Remember, it's vector. Okay, we got to have the positive on it. That's something that gets people on the unit exam a lot. Okay, I give them a simple graph like this and ask them to do exactly the same thing, and they forget to put the vectors on displacement and velocity. Okay, we want to remember that those are vector quantities and absolutely must have the vectors on them. Okay, questions on that? Okay. We are going to do a little bit more y equals mx plus b stuff today, but with velocity versus time graphs. Okay. I want to let you know, guys, that I had to reschedule my back injections for tomorrow, so I will not be here to look over labs tomorrow. If anyone wanted me to look over their labs tomorrow, okay, I will not be here tomorrow, but I'm here all day today. Okay, I can look over them today, scheduled help lunch or after school. Okay. I might be able to have a look at them tomorrow. If you send me an email, I might be able to access my stuff tomorrow. We can try. Last ditch effort. Okay, I can't guarantee anything. Okay. All right. Let's have a look at velocity versus time graphs here. Come on. Okay, so if you can find that in your notes package there, guys, lesson 8.2, and it's now the latter half of it. Okay, so a velocity versus time graph, okay, shows us a little bit different stuff. Okay, still constructed the same. Okay, we're going to have time on the x-axis, but now we're going to have velocity on the y-axis. Okay, so it'll be meters per second on the y-axis. Right. If I have a line, just a regular linear fit like that, okay, here's what I can read directly off the graph. Okay, looking at that graph, I can know how fast and in what direction the object is going at any point in time. I mean, after all, it is a velocity versus time graph. The two things I should be able to read directly off the graph are velocity and time. Okay. Are there some things I can interpret off of this graph? Like based on its shape, can I tell what's going on? Okay, what's the subject include?
You can tell if it's accelerating or decelerating.
Right, I'd be able to tell if it's accelerating or decelerating. On a position versus time graph, what did that look like?
It does look like getting steeper.
Right, it looked like a curve, right? Okay, is it going to look like a curve on this graph?
No.
No. In fact, what's that graph showing right now?
Acceleration.
Yeah. Now, here's the thing about acceleration, okay, because I want to talk to you a bit about the importance of terminology. In physics, the definition of acceleration is any change in velocity. We don't use the term decelerate in physics. Okay? Acceleration can be positive or negative. Okay? So, the word accelerate by its strictest definition means any change in velocity. So if something is slowing down, and this is going to seem really counterintuitive, it is accelerating. Okay? Because up until now, our North American cultural minds have said that accelerate means go faster. Well, actually, accelerate means change your velocity in any way. Okay? All right. So this graph is showing what kind of acceleration? Positive. The object is going faster, right? We can clearly see on this graph that the velocity is becoming bigger in a positive direction. Okay? That's a horizontal line. What is that object doing? Moving at a constant velocity. On a position versus time graph, that would have meant that it was stopped. So does a horizontal line on any graph mean no change?
Yes.
Yeah, it does. Okay? A horizontal line on any type of graph means y isn't changing. Okay? And on this graph, it means traveling at a constant velocity. On a position versus time graph, it means not going anywhere because the position isn't changing. Okay? Everyone kind of follow the logic there? Okay? That's those interpretation skills, okay, that I want you to develop, to be able to look at a graph and know what's going on. Okay? All right. Oh, I skipped over. That's way too far. I went way too far. Sorry, guys. I was like, where's the graph I wanted? And it's right here. It's because I was on the wrong slide. Okay, so velocity versus time graph, okay, helps us to describe whether the velocity of the object is constant, a horizontal line, okay, or the velocity of the object is changing, that would be a diagonal line. Okay, now I'm going to move this diagonal line out of the way. This is a position versus time graph here on the left. What is that object doing? Elliot? Moving forward at a constant, yeah, velocity, speed too. Okay. All right, so it's moving forwards at a constant velocity. What's the velocity versus time graph showing?
Change in velocity.
There's no change in velocity. Okay, the one on the right, right? The one on the right is the...
I thought,
Oh, okay, sorry, you were still looking at this one. Okay, so this one here, we got a horizontal line, right?
yeah.
Are these two graphs showing the same thing?
Yes.
Are they showing exactly the same thing? Maybe we can find out. How can I get the velocity of the object off of the position time graph? Okay, I can find the slope of the line, okay? Because that would be effectively taking final position minus initial position dividing by time, right? Okay, so let's just do this. I can get these numbers all off of the graph, okay? This will be y, okay, right here, it'll be 1400, okay? B is 100. Weird place for the graph to start, but that's where it starts. And how long does that take?
5 seconds.
5 seconds. Okay, so that's going to be 1,300 meters divided by 5 seconds. I'm pretty sure that comes out to 260 meters per second, and it's positive. Is that what the velocity versus time graph is showing? It is. So these two graphs are showing exactly the same object. Okay? Could that be a multiple choice question on the test?
Yes.
Absolutely. Okay? Or I could say, here's a position versus time graph, show you this, and then show you 4 different velocity versus time graphs and ask you, which one's showing the same thing? Okay? That's an interpretation question, right? Being able to determine what is happening on each one of these graphs. Okay? All right. So just looking at that graph, I can definitely tell that, yeah, these are the same things. The 250 line is right here, okay? This is slightly above the 250 line. It's going 260 meters per second for 5 seconds. Okay? It's showing exactly the same thing. Now, I just calculated as well what the total displacement of that object was. Right? I went final position minus initial position. I went 1400 minus 100. Everyone okay with that? Mm-hmm. Could I calculate the displacement of the object on this graph? Okay, let's think about what we have. Do we know how fast the object's going on that graph?
Yes.
Do we know how long it's traveling for?
Yes.
Okay, can I get displacement with those two numbers?
Yes.
Absolutely. Okay, I can do this. V equals d over t, okay? Remembering that that's average velocity is total displacement over total time, okay? And I have these two numbers, all right? So I'm just gonna go v times t equals d. Well, 5 seconds times 260 meters per second, gee, that's kind of like this one here. It better come out to the same number, okay? Should come out to 1,300 meters. Okay, all right, so far we've discovered that we could calculate the displacement of the object on a velocity versus time graph. Okay, we just have to use v equals d over t. We can read the velocity and read the time. Okay, now another thing you guys told me just a minute ago. That object is doing what? It's accelerating. Okay. Could I calculate its acceleration?
Yes.
I could. We haven't done that before. Okay? It's not a formula that we've used yet. Okay? But acceleration is how fast you change your velocity. Okay? Velocity is on the y, time is on the x. What about this line should I calculate if I want to know how fast I'm changing my velocity? The slope. Okay? See, you guys are getting better at it. Okay? You figured it out already. All right? Any graph, if you want to find the rate at which y changes over x, you find the slope. And on this graph, the rate of change of y is meters per second divided by seconds. Okay, now here's a weird one for you. If I divide meters per second by seconds, if I want to divide fractions, what do I have to do?
Go 1 on the bottom.
I have to, okay, put A1 or the 1?
I was gonna say you like flip the second fraction and like times them together.
Right, reciprocate, flip, and multiply. That's how we divide fractions, okay? So right now I'm dividing these fractions. If I want to actually do this, okay, then I'm going to reciprocate the second one. So now it's 1 over s instead of s over 1. What's m times 1?
M.
Meters, right, m. What's seconds times seconds?
Seconds squared.
Seconds squared. Okay, here's what meters per second squared actually means. Meters per second per second. Does that tell me how fast I'm changing my velocity?
Yes.
I'm going this many meters per second faster. Okay, I change my velocity by this many meters per second every second. Okay, meters per second, or we usually just say meters per second squared, are the units for acceleration. Okay? All right, let's see if we can calculate the acceleration of this object. Okay, we're going to use this, same as we did before, because we already established it should be the slope. Okay, what's y? 400. Okay, what's b? 100. Okay, and x is 5 seconds. Okay, so we're going to have 300 seconds over 5 seconds should be 60 meters per second or meters per second squared. Okay, here's the one thing I don't want you to get confused with. Just because that has a square doesn't mean you square the number. Okay, that squared is part of the units. It doesn't affect the base number. Okay, because meters per second squared is just the short way of saying meters per second. Everybody all right with that? Okay, does that seem fast? It's very fast. Okay, to give you a comparison, if you were falling, you'd only be accelerating at 9.81 meters per second. Okay, this is a lot more than that. Okay, it's about 6 times more than, actually a little more than 6 times that. So like 6 Gs, okay, would be the acceleration you'd be experiencing. You'd feel 6 times heavier than normal. if you were accelerating at that rate. So if you've seen Top Gun Maverick, when he pulls out of that dive and he's pulling 9 Gs, okay, he feels 9 times heavier than normal. Well, earlier in that pull out, he would have been probably at 6, okay? And you know, the face pulls back and they black out and all that fun stuff. Yeah. Okay? All right. Is that sort of making sense? Did we do anything new here? This was just y equals mx plus b, right? And we just read some stuff off a graph. If you know your graphing skills, you can use them on any graph. Okay? All right. Another thing to look at. With this line here, could I still calculate the displacement of that object? Even though now it's a diagonal line. I can. And I do it in kind of the same way. When I wanted to calculate the displacement for the horizontal line there, I just said, all right, I'll take average velocity and I'll multiply it by time, and that'll give me the total displacement. Can I still do that here? I can. I just have to calculate the average velocity, which, believe it or not, isn't all that hard. Okay, I'm going to show you a little trick to help you here. When I calculated the displacement for the horizontal line, okay, I took the average velocity, which was 260, and I multiplied it by 5 seconds. What, if that's a rectangle, what did I calculate about it? I went length times width. What does that calculate? It calculates the area, right? So the area underneath the line on this kind of graph is the displacement of the object. Because when you calculate that area, what you're doing is taking the average velocity and multiplying it by time. You're going base time times height, average velocity. Now I've got a diagonal line. Does it make a triangle?
Yeah.
Okay, how do you calculate the area of a triangle?
Base times height.
Base times height divided by 2. Okay, so let's look at that from this perspective here. Okay? This object changes its velocity from 100 to 400. Would its average velocity be halfway in between 100 and 400? Would that be the same as dividing the height of the triangle by 2? That's why it works. Base times height of the triangle over 2. Well, the height of the triangle divided by 2 is the average velocity of the object. Okay? So we're still using this formula. We're just having to calculate the average velocity a little bit differently. Okay? For a rectangle, it's easy. It's just base times height. For a triangle, it's base times height divided by 2. But this is the height over 2, and this is the base. Okay? And it's going to give us the displacement of the object on any velocity versus time graph. Okay? Is there a way for me to check that? Make sure that it worked? On the x-axis, what are my units? Seconds. Okay? And what are my units on the y-axis? Okay. Still get meters, right? Okay. You can always check. Okay? If you've tried something, you're looking and you go, I think I did that right. Plug the units into the same calculation and see if you get the units for what you were looking for. It's always a good way to double check your math. Okay? All right. Everybody okay with that so far? We're going to spend lots of time working on all different ways to do this today. Okay? But that's the stuff we can get from the velocity versus time graph.
So that would be like 250.
So we'd have 400 minus 100, so the height would be 300, right? Over 2, so 150. So the height over 2 is 150 times 5. Okay, so 750, I think. I could be wrong. I shouldn't do math in my head, especially on a Monday morning without coffee. computer thinks it's Monday. All right, mental math was okay today. Okay, so that object is going to travel 750 meters while accelerating from 100 meters per second to 450 meters per second. Okay, everybody all right with that? Okay. Would what we do change if we had a graph that had like shapes all over it? What if I had a graph, a velocity versus time graph? That did that? Could I still use the same thing we just did? I absolutely could. I just have to break the graph up into shapes. Yeah. Okay. I could do a rectangle here. Okay. Triangle there. Triangle there. Rectangle. Triangle. Triangle. Rectangle. Okay. If I calculate the area of all of those, what I'm doing is using the average velocity for each part and multiplying it by the time for each part, okay, and getting the displacement for each section, and then I'd add them all together, making sure that I kept the negative ones negative, right? Because below the x-axis, there's that little bit there that would be negative. Okay? All right, so in this part of the graph here, object's doing what? It's horizontal. Constant velocity in a positive direction. Okay, what's it doing here?
Accelerating.
Accelerating in a negative direction. Okay. And if I put some times on here, well, that was supposed to be a 1. I got ahead of myself. Not 1, 2, 3, 4, 5, 6, 7. Okay. During this part of the acceleration, okay, from A to B, does the object change direction? Yeah, right? I mean, for part of that, it's above the x-axis, which means it's moving in a forward direction, a positive direction. But then it goes below the x-axis and is traveling in a negative direction. So at what time does it actually change direction? 3 seconds. Okay? And how fast is it going at 3 seconds?
0.
0. Okay? If I throw something up in the air, when it's at its maximum height, it's going how fast?
0.
0. Okay? Anytime you've got something that starts in one direction, okay, but is accelerating in the opposite direction, it's going to slow down, slow down, slow down, come to a stop for an instant, and then start to go in the direction it was actually accelerating. Okay? This would be like if I had like a bungee cord stretched across the front of the room and I just ran at it. Okay? As soon as I hit that bungee cord, what does it start to do to me? Yeah, it starts to slow me down, which means I'm actually accelerating backwards. Okay? And I'll slow down and I'll slow down, and at time 3 seconds I will stop, and then the bungee cord will shoot me in the other direction. Okay? I'm still the same rate of acceleration. The bungee cord is still pushing on me. Okay? But now I'm actually going in the direction I'm accelerating. Okay? That sort of makes sense? Okay? Velocity versus time graph, there's a lot more to them. There's a bit more interpretation to them. Okay? All right. Okay. Graph of a person running a race. Okay? What are they doing between 0 and, let's say, 5 seconds? Accelerating. Okay. What are they doing here between 5 and 10? Okay. And then what?
Accelerating negatively.
Right. Do they come to a stop?
Yes.
I see their velocity becoming 0 at the end of that line. Definitely they come to a stop. Okay. Is this a typical shape for someone running a short race?
Yes.
It is, yeah. For the first, well, it's actually maybe a little atypical. If you're running 100 meters, most people are actually accelerating for somewhere between 40 and 60% of the race. Okay? They actually only run at their top speed, okay, for a short part of the race, depending on who the runner is. But most of the time, you actually accelerate for much of the race, and then you only get to run at your top speed for a short amount of time. Okay? Now, does this person run very fast? They're kind of mid. Okay? Like, that's 8 meters per second. Believe it or not, that's not that fast. Usain Bolt can run at more than twice that. Okay? When he's at his maximum speed, he is running at nearly 17 meters per second. Okay? I mean, dude was a freak of nature. Okay? Like 6'7", okay, long legs, like the whole works. Like, yeah, he could really motor. All right?
That's a lot of meters.
It is a lot of meters. Now, to give you an idea, that means he could cover from this wall across the hallway and halfway through the lab on the other side in 1 second. Okay? And that would probably take him, let's say, 2.5, 3 steps. Okay? Usain Bolt had this freakish thing. He could run the 100 meters in 34 strides. Okay? And keep in mind that like 12 of those are in the first 10 meters. Okay? Like the guy had a long stride. When you're going 17 meters per second, you lift up your leg, you fly a little ways, and before the foot comes back down and starts pulling again. Okay? So dude was pretty fast. And the 100 meters wasn't his good race. He was actually a far better 200-meter runner because he was actually a terrible accelerator. Okay? Usain Bolt's graph would not have looked like this. Okay? Usain Bolt's graph would have looked like this. Okay? Because he was so tall, he wasn't as powerful as some of the smaller guys. Like, you look at sprinters and they come in 2 types. Well, 2.5 types. Andre DeGrasse is kind of an exception too. He's kind of short and skinny. Okay? But most sprinters are either short and powerful, so really thick and muscular, or they're built like Usain Bolt, Donovan Bailey, that type. They're tall, they're 6'3" to 6'7", okay, and they're skinnier. Okay? Those guys are not usually as powerful, but they're fast when they get to their top speeds. Okay? The other type is short and powerful. Those guys can really powerfully accelerate so they can get to their top speed faster, but their top speed isn't as fast. So oftentimes when you'd see Usain Bolt run, he would start out in last. He was also a terrible starter. I mean, if anyone could have ever fixed his start, his acceleration, imagine what he could have done. Okay? But he actually, you could see anyone running against him when he was running, they'd always be doing this. Because they knew he was coming, okay? Because he was always accelerating because he was just a slow accelerator. But once he got to that top speed was so much faster than everybody else's. He'd just reel everybody in. Okay? In the 200 meter, it was even more evident. Okay? Once he got to his top speed, it was like, see ya, okay? Because no one was going to catch him. Okay? He was just freakishly athletic. Okay? Does that sort of make sense? This is actually something that, like in track and field and in hockey and in football, okay, anything where acceleration and power are important, okay, like if in football they make you run the 40, okay, in hockey they have you do those kind of like wind sprint kind of things where they're timing you. They're looking at what is your power versus speed kind of ratio, and then they can tailor your workouts to building the part that's weaker, okay, or they can tailor your race if you're running a race so that you can be the most efficient possible rather than try to change Usain Bolt into a freakishly muscular massive thing. Okay, that wouldn't work for him. His frame wouldn't hold it. Okay, you're better to accentuate his strengths. Okay, that sort of makes sense. There's actually a lot of science that goes into sport like that. Okay. Let's have a look at this graph here. Okay? What's the slope of this graph?
0.
Why?
Because it's moving at a constant positive velocity.
Because it's moving at a constant positive velocity. It's not accelerating, right? We know that the slope of this graph is going to be the acceleration of the object. In this case, the object's not accelerating, so slope is 0. Okay? Could that be a multiple choice question? Mm-hmm. Easily, yeah. Okay, what's the displacement of this object over the 10 seconds? Ooh.
50 meters?
50 meters. Okay, remember, if I want to calculate displacement, I just manipulate v equals d over t. Do I know what v is?
Yes.
Yeah. Okay, it tells me right here. Okay? Y-intercept is 5 and it's a flat line. So the average velocity is 5 meters per second. Does that for 10 seconds. Total displacement is positive 50 meters. Okay, don't forget the vectors. Okay. Okay. What's the acceleration of this object? 2.96 meters per second squared. Positive or negative? Do you need to have that on acceleration?
Yes.
Acceleration is a vector quantity. Okay. What's the initial velocity of this object?
0.
Nope. Negative 0.182. Okay. Remember what b is, right? B is the y-intercept. It's the value of y when x is right. So in this case, when x is 0, I'm looking at my initial velocity. Okay, that means y would represent my final velocity, right? If I'm looking at y equals m times x plus b, okay, if b is my initial velocity, y would be my final velocity. It's the last value of y that I'm working with. Okay, what did we say x was?
Time.
Time. Okay, and m is?
Slope. Acceleration.
Is acceleration. Okay, so I'm going to show you something here. If I calculate the slope of this line, slope of a line on any graph, it's y minus b over x. Okay? We just said that y equals final velocity, right? What did b equal? Initial velocity. What did x equal? Okay, on the back of your periodic table is that formula. Okay, that is how we calculate acceleration. Okay, that is why the slope of the line on this graph is acceleration. Okay, it is the rate at which you are changing your velocity.
We'd be allowed to use our periodic table on like tests?
Oh yeah, absolutely. It's your formula sheet. Yeah, I don't want you to memorize all the formulas. Please don't. Okay? You don't need to. On the Physics 30 diploma exam, you get a data booklet that I kid you not is this thing. Okay? And it contains all the formulas, a periodic table, constants, all kinds of things. So, yeah, we do not require you to memorize anything, periodic table, any of that. Okay?
Are we allowed to just write like the n equals y minus b over x on the periodic table?
No. You have y equals mx plus b on there already. So here's, guys, this is the caution I give you. On your unit exam, I'm putting the formulas that are on your sheet on the front page of the unit exam. You have to be able to do the algebra. Because what I often find is people like, I hate algebra, so I'm just going to write all the manipulations of every formula on my formula sheet. Well, then you don't learn how to do algebra, and then when I give you the formulas on the test and you don't have your sheet with all the cheats on it, it works out badly. Okay? So don't go writing all the manipulations of every formula on your formula sheet. Learn to do the algebra. Yeah. Okay. Let's look at a different one here. Okay. So for this one here, what's the acceleration of this object? Meters per second squared. What's missing in front of the 3.3? Positive 3.3 meters per second squared. Okay, what's the initial velocity of this object? Okay, 4.14. Okay, calculate this for me right now. What's the velocity of this object after 25 seconds? You have everything you need on the board right now. Okay, I want you to calculate for me the velocity of this object after 25 seconds. Okay, how do we go about doing that?
y equals mx, so, or mx plus b.
Right.
Because velocity is y in this case. So we do 3.3 times 25. 25, because that's the seconds we need, and we add 4.
Exactly. Okay, we use y equals mx plus b. I asked you to calculate a y value and I gave you an x value. Okay, so basically I'm just saying, yes, use y equals m times x plus b. In fact, you don't even have to manipulate it. I asked you to solve for y, I gave you an x. Okay, so all you had to do is go y equals, okay, 3.3 times 25 plus 4.14. Okay. All right, so after 25 seconds, it should be moving at positive 86.64 meters per second. Okay, when we did that, okay, we took this formula and we manipulated it for what? Final velocity. We know what the initial velocity is because it's v. Okay? So really what we did is said Vf equals a times t plus vi. We just manipulated that formula, okay, or used y equals mx plus b, okay, to calculate that. All right, calculate this for me. How long will it take to reach a velocity of 150 meters per second? How long to reach a velocity of 150 meters per second? Okay, if I'm asking how long, am I solving for y or x? X, because time is on the x-axis. All right, so I've got to take this formula, I've got to manipulate it for x. So the first thing I got to do is subtract b, okay, and then divide m, and that'll solve for x. Okay, we said 150 meters per second, okay, minus 4.14, okay, divided by 3.3. Okay, so that should take 44.2 seconds. Okay, if you got a different number, remember that you have to do that top part in brackets. If you just go 150 minus 4.14 and then divide by 3.3, you get a different answer. Okay, because your calculator does order of operations, so it divides the 4.14 first, okay, and then subtracts that from 150. So make sure that's what I did here, is I just did the top, got the answer, and then divided the top by the bottom to make sure I get what I'm supposed to get. Okay? Everybody all right with that? Okay, last thing we want to do on this graph. I want to calculate the total displacement of this object to 10 seconds. Okay? Now, we said before that we would have to calculate what? Or draw what?
Shapes.
We'd have to put shapes on here. How many shapes are on this graph? There are 2 shapes on this graph. Does the graph start at 0?
No.
Okay. So that means there's a rectangle under that triangle. Okay? Because the object doesn't start from rest, doesn't start from 0. So what we have to do is, yeah, we can find the area of this triangle. That will be the distance the object covers, or the displacement of the object while accelerating. But we also have to take into account how far it would have gone given that it was already moving at time 0. Okay, so it's something to watch for because it happens a lot with velocity versus time graphs. If your y-intercept isn't 0, then you've got a rectangle under your triangle. Okay, you have to kind of watch for that. Okay, so what we're doing with the rectangle here is we're taking an average velocity of what? What's this number right here? 4.14. Okay, so we're saying it started at 4.14 and did that for 10 seconds. Okay, so that's going to be 41.4 meters. And then I've got the triangle. Okay, now, do I know how high the triangle is at the end?
No.
Can I calculate it?
Yes.
Yes. Okay, now, how would I do that?
So you calculate how, what its velocity would be at 25 seconds.
Not at 25, at 10.
Yeah, but like the same way.
The same, oh yes, absolutely. The same way as we did when we were calculating the velocity at 20. Yes, absolutely. We're going to calculate y. Okay, we're going to say, all right, what's y? 3.3, okay, times 10 seconds. Here's the trick though. If I calculate y at 10 seconds, I'm adding on the height of the rectangle. Right? Because I'm about to go plus 4.14. Is that how tall my triangle is? That's what y is at 10 seconds, but it's not how tall my triangle is. My triangle starts at 4.14. So should I add this 4.14 on? No, I shouldn't. It's just geometry. Okay? It's just a matter of looking at this and going, oh, I'm calculating y. That's from the x-axis to y. Okay? Not from the bottom of the triangle to y. Okay? So in this case, I wouldn't put that in there. Okay? Because I only want the height of the triangle. So that's just going to be 33. Okay? And my base is 10. Right? So if I want to calculate the area of the triangle, it's 33 times 10 over 2. Base times height over 2. Okay? So 33 times 10, okay, is going to be 333. Okay? Over 2. I'm not going to do that in my head. Okay? So 166. Was it 0.5? Yeah. 0.5 meters. Okay, what do I do with those two numbers? Add them up. Okay, that's my total displacement.
Why did you multiply it by 10 again?
Because I got to go base times height. I just did this to calculate the height,
Oh,
right? Once I had the height, and then I can do my geometry. Does that make sense? Okay. I know, it looks like I did the same thing twice, because I did. Yeah.
How did you get 333?
I took the height of the triangle,
Yeah.
33,
Yeah.
and I multiplied it by the base of the triangle,
Or
10
just
seconds. 10.
So that'd be 3.
Okay, so I know, because of the way this worked, it looks like I did the same thing twice. First I had to calculate how high the triangle was. So I went y equals m times x. Okay, that gave me the height of the triangle. Then I took the height of the triangle and multiplied it by 10, the time. I went average velocity times time. So yes, in this case I did the same number twice. It won't always look that way. It just happened to work out was the way I drew this one.
Wait, where did the extra 3 come from? Like
Oh, it should be
That's what
330.
I'm wondering.
That's what, and you have every right to wonder that, because that is a total brain fart on Coderre's part. And right after that, Coderre's going to challenge himself by doing mental math, which I'm pretty sure is right. Okay. All right. So we've got 41.4 plus 165. Good catch, guys. Okay. And we've got our final answer. Okay. We add those two together, and we've got the total displacement of that object. Are you going to have to do some geometry with these graphs?
Yes.
Yes. I'm going to throw some that are going to have like 4 triangles and 3 rectangles, and you're just going to have to do some base times height over 2. On a test, am I going to give you one that's got 4 triangles and 3 rectangles?
No.
No, I'd probably give you one of each. Okay, as long as you can tell me that, hey, Coderre, I remember how to do this. That's what I'm concerned with. Okay, now we have to remember here. I'm kind of teaching you a little trick, okay, to help you with this. But I need you to remember that when we do this, we are still at the very end of it, just doing average velocity times time to get our displacement. With a triangle, we're using half the height. That's the average velocity. With a rectangle, it's just the height because the velocity doesn't change. Okay? I need you to remember that that in the end is what we're actually doing. We just use the area thing because it's easier to remember. Okay? All right, I'm going to give you about a 5-minute break here, and then we're going to try a few more. It was about 15 seconds longer.
That's a long time.
It was very late in 9:27 when I said you could have a break. Now it's 9:33. Pretty sure my math works out there. Okay, what's this object doing?
Accelerating negatively.
Accelerating negatively. Okay. At what rate?
Negative 3.02.
Negative 3.02
Negative
meters per second squared. Okay. Can we calculate the displacement here?
Yes.
We can. Okay. But what do we not know for sure that we might have to calculate?
The initial height?
Well, actually, we have the initial height because we know what b is, right? So b is telling us the initial velocity is 27.5. Okay.
The final velocity?
Well, according to the line, the final velocity is 0. What do I not know right here? I don't know the time. Right? I'd have to estimate it if I was just looking at the graph. Can I calculate what time it is when the object gets to 0? I'm solving for x. Okay. Once I have x, can I do the whole area thing?
Yeah.
I can. All right. That happens sometimes. Okay. This is just kind of another situation where we got to recognize. Okay, I have b, so I know what the initial velocity is. I know the line and the graph ends at, well, the line goes in there at some time I don't know, but I know its final velocity on the line is 0. Okay, so I should be able to calculate then how long it took to get to a velocity of 0. Okay, and that's the thing I'm missing. I don't have the base of this triangle, do I? Okay, but I can calculate it. Okay, so the first thing I've got to do is take y equals mx plus b, okay, and solve for x. So y minus b over m equals x. The final y value is 0. The initial y value is 27.5. Okay, and m is negative. That's good catch. 8.02. Except I'm an old man and snap my back, but okay. Yeah.
It was a demonstration of gravity.
And it was a demonstration of gravity for a short period. Hey, gravity also compresses the discs in your back as you get older. It's fun. Okay, so can I do that calculation now? Okay, so that'll get me, okay, my time to get to 0. All right, so we'll have 0 minus 27.5, okay, divided by negative 3.02. Is it important to have all the negatives in there?
Yeah.
Yeah, because otherwise I'll get a negative time, which means I went back in time, and I'm pretty sure that's not what's going on this graph. Okay? All right, so it takes 9.1 seconds. If I'm looking at that graph, that looks about right.
Yeah.
Okay, if I was going to estimate, I'd have thought it would have been around 9 seconds. So, okay, that seems like a reasonable number, 9.10 seconds. Okay, now, do I only have one shape here? Yeah, I just have the triangle. That's all there is on this graph. Okay, so if I want to calculate the displacement between 0 and when I get to 0 meters per second, that'll be that triangle. Okay, I know the height of that triangle is 27.5. Okay, and now I know that this part of the triangle is 9.10. Okay, so if I go average velocity times time equals displacement, that's going to be the height over 2 times 9.10 seconds. Okay, so okay, what did I mess up? It's a trick, I didn't mess anything up. Come on. Think I make a mistake up here? I never make mistakes up here. Okay, is it okay that my displacement's positive? Yes, it is. Does that seem weird in that it's accelerating negatively?
Yes.
Okay, it might be accelerating negatively, but are there any negative velocities on this graph? No. This object is moving forwards the entire time. It's slowing down, but it's still moving forwards. Okay, so again, if we go back to that, I put a bungee cord across the front of the classroom. Okay, when I first hit that bungee cord, I'm accelerating backwards, but I'm still moving forward. So my displacement should still be positive. Okay, these are the little things we want you to be able to visualize and understand. Okay, because they're the kind of things that come up when we ask interpretation of graph kind of questions. Okay. All right, I want you to calculate something for me. This is using the equation for the line now. Okay, I would like you to calculate for me what the velocity will be at 30 seconds. Okay, calculate for me what the velocity of this object will be at 30 seconds. Okay, we're looking for how fast it's going, or what its velocity is at 30 seconds. Am I solving for y or x?
And why?
Solving for y. Okay, velocity is on the y-axis. Okay, so I'm just plugging in my numbers here. That's going to be negative 3.02 times 30 seconds, okay, plus 27.5. Okay, is it okay that we get a negative number here?
Yeah.
It absolutely is. Obviously, at time 0, it's at, or at time 9.1 seconds, it's already at 0. So it's definitely going to be going backwards after that. Okay, so negative 63.1 meters per second would be our velocity at 30 seconds. Okay. At what time, turn the recording back on. At what time will the object be moving at 15 meters per second? So when will the object be traveling at positive 15 meters per second? Okay, if I ask you when something happens, what am I asking you to calculate? Time. Okay, and time is on? X-axis. All right, so I'm looking for x here. Okay, that's going to be y minus b over m. Okay, we said that when it would be going 15 meters per second, okay, minus 27.5, okay, divided by negative 3.02. Again, here's where that negative is important. If you forget it, you'll get a negative time. Okay, so 15 minus 27.5, okay, and then divide that by negative 3.02. All right, so that should happen at 4.14 seconds. That seems about right, yeah. Okay, somewhere in there. Okay, everybody all right with that? Okay, so that's just y equals mx plus b stuff, okay, but it's applied to this type of graph. Okay. Now we got an irregular graph. Does that change what we do? Whoops, sorry, that's position versus time graph. That definitely changes what we do. Yeah, we did those ones already, didn't we? That's position. Okay. All right, here's a velocity versus time graph. Now I can't use y equals mx plus b, can I? No, I can't. There's no one single line here, okay? And I have no equation on the graph. So I can't use y equals mx plus b anymore. Okay, now we learned just a minute ago, okay, that on this graph, the slope represented acceleration because it was really just our formula for acceleration. If I have an irregular graph, I can't use this formula because I don't have those numbers. But can I get all of these numbers off of this graph?
Yes.
Yes. Okay, so if I'm looking at A here, where they want to calculate the acceleration between 12 and 14 seconds, I need to know how fast it's going at 12, how fast it's going at 14, and how much time is there between 12 and 14 seconds? 2 seconds. Can I find all the parts of that formula?
Yep.
Absolutely. Okay, so if I want to do part A here, I'm just going to go A equals, so at my final velocity, so at 14 seconds, negative 6. Okay, at 12 seconds, positive 2. And that takes 2 seconds. So negative 6 minus 2 is negative 8. Okay, negative 8 over 2 should give me negative 4 meters per second squared. Okay, does that fit with what's on the graph? shows an object accelerating in a negative direction between 12 and 14 seconds. Okay, everybody all right with that? Okay, so if we don't have this formula, okay, if we don't have the equation for the line, that's okay. We can still use this formula because we can read velocity and time directly off of this graph. Okay? All right, total displacement to 20 seconds. Is there a little geometry here? Yeah. There's a lot of geometry here. Okay, so let's have a look at it. What shape do I draw here? What's the object doing right here? Constant velocity of? Zero. What's it doing? Not moving. I can't have a displacement if I'm not moving. Would you agree? Okay. Remember, those shapes we draw are always between the line and the x-axis. This line is on the x-axis. There's no shape to draw there. Okay. So, right here, this object is in a negative direction. All right. So I'm going to draw a shape for that. Okay, and then here the object is accelerating in a positive direction, so I better draw a shape for that. Okay, where is it accelerating faster, here or here? Below or above? Below. Yeah, the line is steeper. Slope represents acceleration. Okay, then I've got this triangle here, and then this rectangle, and this little tiny triangle there. Okay, and then I've got that really tall triangle, and then this triangle, and a rectangle under it, and then that triangle there. And then do I have the same situation at the end as I had at the beginning there for the last second? Okay. Can we find the areas of all those shapes?
Yeah.
Okay, get to it then. I'll come back and we'll do those in a few minutes. Okay, but you got a little grade 7 geometry to do right now. Okay, so if we want to calculate the total displacement, we need the area of all those shapes, because in each one of those shapes, it's traveling at a different average velocity, or doing something different. So we have to treat each one like a separate average velocity times time calculation. Okay, so for this first triangle here, the height of the triangle is -3, the base of the triangle is 3, so 3 times -3 is 9, but because it's a triangle, we divide it by 2, so we know that this is -4.5 meters. Okay. Our next triangle is still -3 high, but it's only 1 second on the base. -3 times 1 is -3. It's a triangle, divided by 2, and we've got -1.5 meters for that triangle. Okay, then we've got this triangle here that's above the x-axis. It's got a base of 1 and a height of 2. So 2 times 1 is 2, divided by 2, because it's a triangle, is +1 meter. Then we've got this rectangle that's 2 high, and 1, 2, 3, 4, 5 on the base, so that should be 10. Okay, and then what's the x value for this little triangle? It's half a second, yeah. And it's not a full block, so it's half a second. Okay, 2 high times the base, 1/2 is 1. Okay, and then divide that by 2. This here is 0.5 meters, and it's positive. Okay, that means that this tall triangle has a base of 1.5. Okay, and it's -6 high, so -6 times 1.5 is -9. Divide that by 2. Okay, and you got -4.5 meters. Okay, then we have this triangle here, which is 1, 2, 3, 4, -4 high, and 2 on the base. So -4 times 2 is 8. It's a triangle divided by 2. -4 meters there. Okay, and then we've got this rectangle here that's -2 high and 4 on the base. That's -8 meters. Okay, and then this little triangle here that's -2 high times a base of 1. Okay, so that's -2. It's a triangle divided by 2 is -1 meter, and then we have nothing there. All right, what do I do with all those numbers? Add them up.
Together.
Should come up to -12 meters.
For the last rectangle there, why are you taking everything from 14 seconds to 18 seconds?
Because that that's what that rectangle is. I did the triangle above it, right? Could I, like, if I'd have gone all the way down to here, then I'd have had like other triangles that had more shapes to do. That's why I cut the triangle off, this triangle here, I cut it off here, so that I'd have a rectangle underneath it. Yeah?
So if it's below the x-axis, it's always negative,
Yeah.
even if it's going up?
Yeah. Yeah, because we're still, like on this graph, if it's below the x-axis, we're moving backwards. The velocity is negative if it's below, so I'm still moving backwards. My displacement will be negative. Does that make sense? Okay, now guys, for average velocity, did I do all the work for that already?
Yes.
Okay, so I just have to go average velocity divided, or sorry, total displacement divided by 20. That'll give me negative 0.6 meters per second. Okay, acceleration, how do we do that? Yeah, use this formula right here. Okay, that'll always work on a velocity time graph. Okay, average speed, take all these numbers, but they're all what? Positive. That'll get you your total distance divided by the total time. Okay, this is what you guys are going to be working on tomorrow with my sub. Okay, I'm going to print out some sheets, and you guys are going to be just working on those. If there's some that you don't get, they'll have like a recording of me going through questions from that sheet, but if yours isn't on there, or it still doesn't make sense, circle it and ask about it on Wednesday. Okay, make sure we go over any questions that come up while I'm not here on Wednesday. Okay? All right, good work today, guys.
Thank you.